Good afternoon. Welcome to this talk. Today, we are very happy to have Yuhai Wu from Toronto to give a talk on some recent work on deep reinforcement learning. Yuhai is an intern at OpenAI in the summer. So before he goes back to Toronto to start his third year PhD, we distracted him a little bit and invited him to come to Redmond to visit for a few days. And Yuhai has a very amazing record of publication in his 2 years PhD. He has 5 NIPS papers and some other ICR papers already. And this work is one of the papers is going to present at NIPS this year. So I hope you enjoyed it.
All right. Yeah, thanks for the introduction. All right, so today I'm going to talk about some recent work that me and my collaborators have developed for deep reinforcement learning using some previous developed method called K-FAC. So it's a joint work with Elman, Shun, Roger Gross, and Jimmy Ba. All right, so I guess most of you have some experience with training deep neural networks. But most of the times these days they're still trained using the first order method, some variant of stochastic gradient descent, such as Adam, Armstrong, Ettergrad. But this first order method has suffered from this well-known problem, which is you usually just go bouncing around a lot in the high curvature directions, but making very slow progress on the low curvature directions. And so this is caused by the curvature is very badly conditioned. So before I talk about my work, I would just give you some backgrounds and then for the background material, I think the very interesting, the very important notion is the notion of a norm in optimization. So basically, gradient descent is just a special case of steepest descent. So the steepest descent is trying to find a direction that that give you a maximum increase in your objective function, steepest ascent, subject to the constraint that the norm of the change is less or equal to 1. So there comes this notion of the norm. And this term here is very important because different methods could be derived from using different norm using the same framework, which is steepest ascent. So for example, gradient ascent is just a special case where the norm is chosen to be the Euclidean norm. And but this norm it has some problems because it depends on the underlying parameterization of the model. So basically, what we are trying to do is that we want to optimize in the space of functions, but we could not do that directly. We have to rely on some parameterization of the models. So basically, the weights and biases of the neural networks. So for example, but this has some problems because, for example, if we want to use a parameterization for the sphere, then we create a lot of distance, some distortion in the distance, and we actually hoped. What we actually want is to do the optimization on the space of functions. So basically compute the gradients and do the optimization on the globe, but not on the flat map. And natural gradient provides a way of doing this. So natural gradient provides a way of doing the optimization directly on the globe. Okay, so basically the analog of the globe and the map is for the neural networks is that we want to define some sort of distance metric on the space of functions. And the natural definition of that, a natural definition is basically you first try to define a dissimilarity metric on a space on the output of the neural networks. So basically, if I want to measure the distance of two functions, I look at, for the given input, what's the difference of the output for these two functions, and then I integrate over my domain, the input domain, according to its input distribution. So basically, for example, here I have two one-variable function f and g, and if I want to measure their distance, basically I try to calculate the square. So for example, if I use this Euclidean L2 distance, then I will just calculate the difference between the two and integrate over the input distribution. And this is just this d, f, and g here. Okay, but this distance is usually, so if this nonlinear function d here is very hard to deal with. So in most of the time, we just use a second-order Taylor approximation to this function, to this metric d here. And what we get is this PSD matrix G, which define a norm on a space of functions. So this function G here is called generalized Gauss-Newton matrix. And if some of you, if this is, if the dissimilarity matrix that we use for the output space is the L2 norm, then this G here boils down to the Gauss-Newton matrix, as we all know about it. Any questions at this point? Right, so basically, we define a metric on the output space, and then we take expectation over the input, and then we take the second-order approximation to that metric, and we get this generalized Gauss-Newton matrix. So this is using, so here I'm showing one example of this generalized Gauss-Newton matrix, which is using the L2 norm. But for the function, for the object that we really care about, which is the neural networks, we actually have a more natural metric on a space, on the output space. So the neural networks, most of the time, they actually define some sort of distribution. So in the case of classification, it's a distribution over the possible labels. But in the case of like RL, reinforcement learning, it's a policy distribution over the possible actions given the current state. So in many cases, it's some sort of function, some sort of distribution. So for distribution, it's a very normal to use KL divergence to define the distance between two distribution. And so basically, if we choose KL divergence in the previous formula, so for the D here, for the rho here, then again we do the second-order approximation to that, and what we get eventually is just the Fischer matrix. So the Fischer matrix is just a metric that it's a second-order approximation to the KL divergence, and it's also defined, can be also defined by taking the covariance matrix of the log likelihood derivative. So this is equivalent definition. Okay, so basically, this Fischer matrix defines a norm, a distance on the space of distribution. So why do we like this? Well, basically, Fischer matrix or Fischer norm is independent of parametrization, and as we can see, usually the Euclidean matrix or other metric that we use is dependent on the parametrization. So here is an example. So if I have two normal distribution, P and Q, and I write it in terms of two parametrization, two famous parametrization. One is the mean and variance parametrization. The other is using the natural parameters, which is also called information form. Then if I just calculate the Euclidean distance between these two distribution, then we actually get different distance. So the Euclidean distance between P and Q is not the same as the Euclidean distance between P and Q parameterized by information form. However, if we calculate the KL divergence, which also corresponds to the Fischer, it's actually the same because it defines in the probabilistic sense. So you always take the integral of P of x times log of P of x divided by Q of x. So this would be always the same. So yeah, so we do prefer some metric that's independent of the parameterization we use because we want to move on the space, we want to optimize the function on the space of functions. We don't want to rely on any arbitrary parameterization we use to, and we want to optimize on the globe, not on the flat map, to avoid any distortion of the distance. Okay, so yeah, so as an illustration here, basically this is the Euclidean gradient we get, and okay, so for optimizing the H theta here, the green line, which is the underlying parameterization. So if we use the Euclidean distance, then this is the direction we get, which is perpendicular to the underlying contour. But then if we use natural gradient, then it will point to a direction which is more meaningful, but it's independent of underlying distribution. So it gives you a more meaningful directions. Okay, so, but of course, so there is many problems with natural gradient. The biggest problem is about how to calculate this Fischer matrix. Well, the Fischer matrix is have dimension number of parameters times the number of parameters, and usually for the modern neural networks, it could have tens or millions of parameters. For example, if I have just 2-layer neural networks, which both of them have like 1,000 units, then I would have 1 million parameters. And then the Fischer matrix is just 1 million times 1 million, which is intractable to calculate, as well as its inverses is also intractable. Okay, so the previous method uses, there have many previous methods to solve this problem. So algorithms like Adam, RMsprop, they're basically trying to approximate the diagonals of the Fischer matrix. They're very, they are indeed have very little overhead, but most of the times we don't see much benefit we can get from them compared to standard SGD with momentum. So another method is like iterative methods like Hessian-free optimization. What they did is that they at each update they perform many steps of conjugate gradient, but that is also that also takes a very long time, and also they have this problem that you can only use the current batch to calculate the approximation to the Fischer matrix. You can never aggregate the history information to calculate the Fischer matrix. And at this point, I will talk about this later on, but this is a very huge point for doing optimization in RL because we care about simple efficiency, and this in particular would cause you many samples to approximate the curvature matrix. And also some subspace methods, they also can be very memory intensive. So what we want, so this is a previous work called K-FAC, which published in 2015. And what they did is that they characterized the problem of calculating K-FAC, to calculate the Fischer matrix as some sort of probabilistic modeling problem. So essentially, Fischer matrix is the covariance matrix of the log likelihood derivatives. And we can use some tools in, for example, graphical models to model this model, like model this probabilistic model of log likelihood derivatives, and basically sample some gradients here and try to model what's the covariance matrix of this distribution. So instead of trying to model the data, we want to model the computation here. So the gradients is we characterize approximating the Fischer matrix as some probabilistic model, of modeling some model of the computation. Right. Okay, so basically we want a distribution that can be compatibly represented, and also its inverses can be efficiently computed. So we make some assumptions here. Basically, we assume that the log likelihood derivatives with respect to different layers are independent. And also the activation and its activation gradients are independent. So I will show you what I mean by this. So basically, what we do, what K-FAC does is that you approximate the Fischer matrix using a blockwise approximation. So basically, instead of approximating the entire matrix, I approximate the Fischer block for each of the layer. So yeah, so this is very specific to the neural network architecture. So how do we do this? Okay, let's say if we have a matrix W for layer L, and its derivative, it will be just the outer product of the backpropagated derivative with respect to the output layer and the activation. So this is just the backpropagation equation. And the way of calculating the Fischer block is that we again do this expectation of the outer product of two log derivatives. And if you substitute this guy into here, then it will just be some outer products of this term. And then if you group them, if you switch the outer, which is allowed for the tensor products, then you will get the tensor product of Kronecker product of this matrix and this matrix here. So another approximation we do is that we approximate this guy using approximate the expectation of two Kronecker products using the Kronecker products of two expectations. So this is how we do it from here to here. And the reason we do this is because we can use some identities to calculate the update equation, which I will show later. But basically, from here to here, we are using the assumption that the activation and its backpropagated derivatives are independent. And these two matrices are here. I'm showing you just how we calculate the L's block Fischer matrix. Yes.
What is the VEC operation?
Oh, the VEC operation is basically just so matrix here. So the gradient here is actually a matrix, right? With respect to a matrix W, and then the VEC means I'm just flattening it out as a huge, yeah, not one hot, like it's just flattening it out.
Yes, one long vector.
Yeah, one long vector. Yes. So because I'm calculating the Fischer matrix, that's like parameter times parameter size. Yes.
In what sense is that an approximation? Like, so expectation of a Kronecker, writing it instead as a Kronecker of expectations?
Yes.
Assuming independence between those two.
Right. So it's not something that, I mean, the underlying parameters of my problem have to satisfy some independent assumption.
Okay. So this is just like a approximation which is wrong that that they make, but actually works in practice.
I see. Yeah.
Yeah.
In practice, how you calculate these expectations? You just sample some input of the neural network and do empirical
Yes,
average.
exactly. Yes. So this is all Monte Carlo samples of these.
So every step, in order to approximate the Fischer matrix, you need to run the neural network a few times.
So in practice, we actually just use one sample, and that just suffice. Yeah.
So you use one sample but average over time.
Sorry? Average over the input.
Average over the input.
Yes. So basically,
every
input distribution.
Batch, you average over the batch.
Yeah. Yes. Average over the batch. Yeah. Yes. The current batch. And so that's a good question. So basically, so when we do the expectation over the input distribution, basically we sort of trying to aggregate a historical information into this. So basically what we do is we keep a moving average of the Fischer statistics to make it more accurate.
But the problem, if you just took 1 or 2 samples, the problem is that your Fischer matrix will be just rank 1 or rank 2. It is not invertible anymore.
No. So, oops. No. So yes, it's rank 1 for one sample.
Yeah.
But then if you aggregate the history information, so basically if you do a moving average,
Okay.
then that's not rank 1.
So every time you compute one sample, but in fact, when you estimate the Fischer matrix, you do average over the history.
Yeah. Yes. So we keep a moving average of that. Okay. Besides that, we also sum over the inputs, right? So that makes it not non-rank 1. Yeah.
Okay.
Yeah.
I have a question. I'm a bit confused by the subscript L. The different L's, are they the same L? The normal L and also the...
Okay, so this L, yes. So these are the same L, yes.
Okay.
And also the W should be WL. So the L's W.
L block.
So yes, the L's, the W for the L's layer. The matrix W for the L's layer. Right. Right, so, yeah, so, I mean, I think the reason we want to do this approximation is given by the next slides. So again, the current Fischer matrix is using this kind of approximation. It's 0 on the off diagonal, but the block is approximated by this Lth block Fischer matrix. And the reason we do this approximation from the expectation to the products of expectation is because we can use these two identities to write the Fischer inverse times a vector gradient to be this form. So basically, first of all, P and Q is just the psi and gamma. And instead of taking the inverse of this huge matrix, so even this block, we do this block approximation, but each block is still huge, right? Because you have the number of parameters of the weights times the of the weights at the Lth layer times that. So it could be still huge. But then if we use this Kronecker approximation to it, it could just be the number of activations times the number of outputs. So these dimensions, the dimension of the psi and the gamma is very small. So instead of taking the entire inverse, we take the inverses of these two small matrices. And we can just calculate the inverse multiply a vector by using this identity here. So this is the mean computation efficiency that gain that we get by making this assumption here. By making the assumption that I said, by making the assumption of expectation of the Kronecker products equal to Kronecker products of the expectation. Is that clear? So again, so this guy here, each block is number of parameters at layer L times the number of parameters at layer L. But these two small matrices, P, for example, or the psi here, is actually number of activations times number of activations. And the lambda here is number of outputs times the number of outputs. And number of outputs times the number of outputs is much smaller than the entire Fischer block matrix. And taking the inverse could be very computational efficient in this way. Yes?
I have a question about another slide. So why did you assume a fully connected network? How did you use that assumption?
Oh, so you're saying, so this is only for fully connected networks?
Yeah.
And yes, okay, so there are ongoing work of developing it for CNNs, RNs. There are
all these derivation, all these formulations at a time.
So I'm presenting to you the first original paper, which only applies to the fully connected network. But then there are follow-up works that basically address the same for convolutional networks, recurrent neural networks.
Okay.
Yes. Oh, you're asking other questions, or?
Yeah, I'm asking. So, do you use the full?
Oh yeah. So the K-FAC
assumption in the formulation chain.
Yes. So the K-FAC is mainly for neural networks. So this approximation here only works for neural networks. So basically, it's a flow like deep learning tool.
I think he's asking like if you change it to CNNs, would the equation still hold?
Oh, so for CNNs, like you basically have sharing parameters. That's the only difference between here.
So is that just a special case of this equation or a different equation?
Oh, you mean this derivatives or?
The CNN version of that statement.
No, so the CNNs would have a complete different form. It will just be sharing parameters, but then you have to aggregate the derivatives altogether.
Okay. Yeah,
But here I'm presenting only for the feed-forward neural networks. Yes. Okay. So yeah. So basically.
So quick question. So if you use a special version of CNN without weight sharing, then this formulation still holds.
Yes. Right. I mean, so essentially, this is okay. So these approximations still holds in CNNs as well. So the computational gain we get is also holds for CNN. In CNN is like the only question is how do we do samples? Like how do we approximate different blocks? Like essentially, it's a sharing parameter, and then you have lots of different copies of the same derivatives. Yeah.
Can you just treat those different copies as samples, different samples?
Yeah. So basically, that's what they did in the CNN's paper. So, but yeah, you should check that. I will give you the pointers later on. Okay. So I think so. This is the approximation they make, and this is the K-FAC updates event for the final K-FAC updates. Basically, it's just the products of three matrices. Although it's still expensive than the first order method, but I will show later that how it compares to the first order in walkout time. It's only 20 to 25% of increase in walkout time. Yeah. Right.
So here you're explicitly computing the inverse times the vector, right? Meaning I understand you have made it very efficient by the factorization assumptions that you have made. But then there's this you had it in your related work section, like the James Martin's Hessian free,
right.
where you can do like TRPO did, like conjugate gradient descent, and then you just utilize the fact that you have an efficient way of computing Fischer vector products, right? So how does this compare usually in your experience in net optimization?
Right. So yes, as I said, there are two ways of doing this. So one is using the Hessian free, right? The Hessian free method, at each time step, they still need to do a lot of computation. So they have an inner loop of computing the conjugate gradient. And that is very slow as well. Right. So for example, if you use TRPO, you can never scale up to like a modern neural networks.
Yeah, they do 10 iterations, right?
Yes, but it's one iteration is like a forward prop and backward prop, right? It's still very expensive to do it. Yeah. But for here, we do this small matrices computation, inverse computation, and then you can do it like asynchronously. So that wouldn't give you too much overhead.
I see.
And also another reason that we prefer this is because I'm also doing a moving average of computing the statistics. But what TRPO is doing is like they can only they're not explicitly constructing the Fischer matrix, so they cannot aggregating the history information. So what they can do is given the current batch, I approximate the Fischer inverse vector update, and usually they require like a 10,000 or even 2,000 batch size, which hurts the sample efficiency basically. I will show you the results later on how it compares to TRPO. Any other questions? So, right. So I guess this is all some backgrounds about K-FAC, and also so K-FAC can be also applied to CNNs or RNNs. So there are this has been published in ICML 2016, And Kronecker factors for RNs are also explored by Jimmy and James. And I think they will release it soon. But I will not discuss them here. Yeah.
So just making sure, in the previous slide,
Yeah.
You're still explicitly inverting the small matrices.
Yes, yes.
Right, okay.
Yeah, we're doing the inverses of the small matrices.
Okay.
The matrices, again, it's just number of activation times number of activations. And it's usually just very small. So
Sure.
yeah. And yeah, right. Yeah.
So that you invert the matrix so that you can multiply that inverted matrix to another vector, right?
Yes.
Can you approximate that matrix vector multiplication without inverting the matrix or even computing the matrix?
So you're saying, can we do direct Fischer inverse vector product?
Yeah, indirect matrix vector product without computing the matrix. Or is
Right. So I mean, the Fischer vector product doesn't do that. The Fischer vector product, which uses just like a forward mode differentiation and then backward mode differentiation, but that requires explicit gradient computation graph. But here, if we made these assumptions, then we cannot utilize these computation graph because we're changing the computation graph. And another thing is, as I said, we actually prefer explicitly constructing these Fischer matrix in order to aggregating the historic information over time. Yeah. Okay. So yeah. So again, so even if we made these assumptions, the K-FAC approximation are still invariant to reparameterization. So these are some. So basically, for example, if I have some reparameterization like point-wise affine transformation, then the K-FAC would give you the same update, whereas the SGD update would be different, compute different functions. So these are also some theory that's presented in the first K-FAC paper.
Point-wise means like every chord. So point-wise is the same as coordinate-wise. So is are you applying a matrix to each weight matrix?
So you're applying to the matrix to each matrix. Yes.
So each weight matrix you conjugate by some.
No. Oh, okay. So it's not the reparameterization we're talking about here is not that complicated. It's just a affine transformation.
So you take a weight matrix.
So take each weight in a weight matrix and just do an affine transform of each one.
Yeah.
That's like
okay.
the same affine
That's
transform.
right.
So you multiply it by constant and add constant.
Yeah. That's
Okay,
right.
okay,
That's right.
okay.
To the elements.
So it's coordinate-wise, not point-wise. It's constant.
Okay, yeah, we should modify the phrasing. Anyway, okay, so, okay, yeah, I'm a bit late, but okay, so let's talk about the main stuff here, which is about reinforcement learning. So basically, in reinforcement learning, we care about sample efficiency. We actually care about sample efficiency more than walk clock time. We have, because in practice, in real world interaction, we hardly can. It's a very hard problem of collecting data for RL. So one way to do this is to use a better optimizer, which can extract more information from a batch of samples. So previous work, such as TRPO, approximate the natural gradient using conjugate gradient, which is also known as the Hessian-free optimization. But they have several problems, as I previously mentioned. They are still very. They still require very expensive iterative updates at each time step, each update. But also they only use the current curvature information for approximating. The current batch for approximating the current curvature information.
Is that expensive iterative procedure, the line search to figure out the KL constraint?
No. The conjugate gradient itself is also very expensive. Yes.
So when they do conjugate gradient, do they require more samples?
Yes, they require more samples for approximating.
If your CG requires 10 steps, then you have to roll out 10 samples.
No, that's not the same. So for doing conjugate gradient, it's just to how well you approximate the Fischer inverse vector product. So the more number of steps you do, is basically a better approximation to the Fischer inverse vector product. But it's not the same as how well the Fischer matrix is. So that's two different problems. One, because Fischer matrix is an expectation of something. So you have to use samples to approximate it. And in the TRPO setting, you can only use the current batch to approximate the Fischer. And that's problematic because you have to use a large batch to do this approximation. And also, it takes several iterations of conjugate gradient to calculate the Fischer inverse vector product. So these are two constraints. But in our case, we can aggregate the historical information to do a better approximation for the Fischer matrix. Is that clear? Or
Yes, right.
okay. Okay. So So what we propose is Actor. So we call Actor which stands for Actor Critic Kronecker-Factored Trust Region method. So basically, let me review a little bit of RL. So we basically apply K-FAC to the Actor Critic methods. So in RL or in Actor Critic methods, the goal is to optimize the expected sum of discounted rewards. And it is parameterized by, the policy is parameterized by some parameter theta. In policy gradient, which basically takes the derivative with respect to the theta directly and gets this policy gradient for doing optimization. And it consists of two elements. One is the advantage function, A pi, and the other is the some policy term. So the A here, which is the advantage function, which is usually consisted of some approximation, some values, some estimate of the values of the current states. So yeah, so basically what I want to say is that there are two components. One is the policy, the other is the value function. Okay, I guess this is familiar to most of you, so maybe I will just go quicker. So what we do is that we apply K-FAC to advantage actor critic, which is also known as the A2C. And A2C is a deterministic and synchronous batch version of A3C. A3C is better known because it's just the asynchronized. It's this word, asynchronous method for deep reinforcement learning, published in 2016. Okay, so why do we use A2C but not A3C? So there are two reasons. One is that we actually don't see too much gain from doing asynchronous updates. And the other thing is that because we want to approximate the Fischer matrix, and it's better to use a large batch size. So if we aggregate all the gradient information together, and that could give you a better approximation to the Kronecker approximated Fischer matrix. Right. So okay, but the other way is to do something like aggregate the Fischer, but then doing asynchronous gradient updates, and that could also be done. Yeah.
What's the deterministic part?
Oh yeah. So basically here. Oh, deterministic part. Okay, deterministic basically means that it's not asynchronous, so it's deterministic.
So it's the same as synchronous.
Right. Oh, okay.
So yeah, it's not exactly the same, right?
I mean, like synchronous makes it deterministic.
Yes,
right?
true. Yes.
But
Yeah.
when you select action, you still
Oh,
use
right.
the
So
stochastic policy, right?
yes. Okay. Yes.
But the deterministic
Exactly.
word doesn't apply to the policy.
Right. Yeah, it's a bit confusing here. But here, yeah, mainly I would want to say is that deterministic means that the algorithm itself doesn't give you any undeterminism. Yes.
So when you say there's not too much gain,
Yeah.
by gain you mean
Speed
training
of
time?
the training time or sample efficiency.
I see.
Both.
Okay.
Yeah. Yes.
So you're saying with A3C you would take as much time as before, but just using like K as many cores, like workers.
Yes, so basically in A2C what we do is that previously you have like, for example, 32 threads that computes each of them collecting like 5 or 20 steps of rods.
Yeah.
So right now we basically aggregate all these gradients together and then do one update instead of doing update by each of the agents. Yeah. So so we don't see too much difference between A2C and A3C. And it's actually, for some reason, for some of the games, we actually see that A2C can give you a better performance, the better performance in the end. So basically, it converges to a better policy in the end. And also, A3C is just asynchronous, and so some problems with the reproducibility problems, like you could not like reproduce it easily. Yeah, so we basically applied K-FAC to A2C. So the way that we do it is by, for Actor, for constructing the Fischer matrix, it's just usual natural policy gradient way. Like this is a very old work, 2003. So we basically just use the policy distribution to calculate the Fischer matrix and over the trajectory distribution. For the critic, so this is some new part that we propose, which is usually people just use like standard optimization for the critic, but we also propose to use K-FAC. So the way we do it is by assuming a normal output distribution of the value function, and use K-FAC to approximate it by this function.
Starting to get lost. What was P of tau again?
Oh, okay. So tau is the trajectory. So it refers to state, action, and reward. Oh, actually, just state action here. It's just
But basically sample from pi.
yeah. So it's just you basically you have 30 threads and 20 steps of rods at each thread, and then you aggregate all of these together. So that's how you approximate the Fischer matrix. And for the critic, it's all the same, but we are using the like a normal output distribution. Basically, we make such assumption, and this is equivalent to Gauss-Newton matrix, Gauss-Newton metric. Yeah. And also we do have some other parts. Which one is that we adopted the distributed implementation of a K-FAC. So this work is done by Jimmy Ba et al. In 2017 ACKTR. And what they did is basically asynchronously compute the matrix inverses. So we have these small matrices and we compute them asynchronously. So basically, in the main thread, you basically pull from the asynchronous thread the latest version of the inverse. So it could be that you are using a stall version of the matrix inverse, but it's okay. Like we don't see any performance difference. And also, we are using TRPO type of rescaling for the learning rate. So in TRPO, they try to say that I want my update makes the policy before and after the policy before and after the update to be not differ by some radius, which is measured by KL divergence metric. And we are also using the same. However, we're just using the Kronecker approximated Fischer matrix to calculate the differences. Is that clear for most of people? So do I need to? Okay, so basically, in the TRPO, what they want to do is like the delta theta, like the change we make, multiply by some by some matrix Fischer, and times the delta theta here. So this quadratic form is less or equal to some radius delta, and my learning rate is alpha. And basically, given the delta, I can recalculate the alpha. So what we do is that we do the same thing, but we use f hat which is the K-FAC approximated Fischer matrix instead of the true Fischer matrix, real Fischer matrix, to rescale the learning rate alpha. And this so we are using this and as well as moving average to accumulate the Fischer statistics, as I explained before. So these are the three technical part we use. Okay, finally I can show some results.
One question.
Yeah.
So I didn't see why in the traditional TRPO they can't use previous samples to do a sample average, like to do a history average.
Okay, so
Why?
could you explain? Could you give any? How do they do it?
And I do not know whether they do it or not, but it's just an expectation. When you do that expectation, you just use previous samples to.
So basically, this is the thing. So, if you do the Fischer inverse vector product, right?
Okay.
You have to calculate both, like basically together. Like it's a mixed thing. So the vector here, you cannot use some previous samples to calculate the v because TRPO is a on-policy method. So if you use the previous samples, then the v here, the gradient information here, becomes biased.
Okay.
So you have to use the current batches to calculate both of them in TRPO. But in our case, the v we always use the current data, the current gradient. But the f is some sort of approximation, although some
Average.
some average moving average.
So the essential reason is that they did not explicitly calculate out the f. So
yes.
they just do some some fast way to kind of the CG to calculate the f inverse based
Exactly.
Okay.
So they're not explicitly constructing the f,
Okay.
which is a disadvantage, but also an advantage. If you but then another thing is that TRPO is very slow, and I will show you here, which is this LORAT. So basically, we're comparing Actor, which is our method, and A2C and TRPO. TRPO is the green line. So here you see that TRPO basically doesn't quite learn on most of these games, the Atari games, and I believe no one actually succeed in training the Atari games using TRPO. The reason is that it's just it's not easy to train convolutional neural networks using TRPO, and also so here we're actually not using convolutional neural networks because it takes too long for computing even one update. So what we did is using like a MLP, and that's probably the reason that it couldn't learn for these games. But it's just it's also and also like so the Actor compared to the baseline A2C is like 2 to 3x speed up in terms of sample efficiency. So the x-axis here is the number of time steps, which is also refers to the number of frames that you see in the for the agent. So the number of one time step refers to 4 frames. So this time step is not the time step for updates. It's just some terminology we use. So basically, one time step refers to 4 frames. Yes.
So for your method, do you use convolution net or?
Yeah. For our method, we use convolution neural network. We just use the DQNN architecture, which is 32, 64, 64, 5112. It's a very standard architecture.
Then in order to apply the K-FAC approximation, then the formula will be different from the one that.
So I presented the fully connected version, but then it's basically also developed in 2016, which is used for convolutional neural networks. Yes.
In your previous, you mentioned that you use moving average
Yes.
to compute
Fischer
features,
statistics.
statistics.
Yes.
Why moving average? Why moving? I can understand that you put more weight in the current sample.
Yes.
But it's not entirely clear to me why you put
because
more weight in the recent samples previously.
It's actually so if we use past samples to approximate. So because we care about the current curvature, so that's why. So like you're on the current like you're at a point on the current loss surface, right? You want to approximate some curvature information at the current point, but not the past point. So the Fischer matrix is actually biased in some sense if we use moving average. We do actually only want the current batch to approximate the Fischer matrix. But in practice, we actually find the historical information can help to approximate better.
Yeah, you use historical information,
Yeah.
but you use moving average.
Yeah, so okay,
rather
so
than just vanilla average. So that
no. So this term here, P of the trajectory here, is basically using the current policy.
Right.
So this expectation is only means it's respect to the current batch of data. It's not the previous data.
So what do you mean by moving average here?
Oh, moving average is
So
just
it's the first
right.
step, and then you have multiple batches.
Yeah. So the moving average means you have a exponential average. Is that? Yeah. So like does that make sense? So like a momentum. Yeah. Is that like a momentum?
It's like the way we calculate moving average in our RMS probe.
Yeah, RMS probe. Or like momentum. Yeah.
Not average of moving window.
No. So it's just a momentum.
so yeah, similar to momentum.
Yeah.
Okay.
So yeah. Oh, okay. Sorry, yeah. So right.
By the way, are these results better than state of the art?
Yeah. So this is the state of art.
Okay.
So these are the state of art results on Atari games. We have so basically we do see a lot of improvements in terms of sample efficiency compared to A2C. That's it. And they are in terms of okay. So I can show you a video. So the left hand side is the A2C, and this is Actor on the same when using the same number of samples to train them. And you can see Actor can actually perform very well using the same number of samples. And this is the score. You can actually see that the Actor can get to like over 15,000 on the Qbert game in less than 24 hours of training. Okay, yeah. Oh, and also we also did experiments on continuous control, which is the MuJoCo benchmarks. And usually the most simple, most standard case is when we use the state space as the inputs. So for example, the joints and very low dimensional inputs for doing the control. And we see that there are also many improvements. So the blue line is the Actor compared to the other two methods. So in TRPO, actually, in this case, it's actually performing better because it's a low dimensional problem. So the control, the policy could be even linear. So in this case, TRPO can get better. But it's still the Actor still wins over.
So I have one question actually. So the two big differences is with TRPO with respect to Actor is that TRPO is not using a CNN in the Atari games, and you are.
Yeah.
So and the other one is like in at least in A to C kind of approaches and A3C, you have a number of diverse universes, right? Like parallel universes in which you are gaining experience and aggregating the gradients, right? So do you have something similar you have imposed on TRPO?
TRPO, you mean like parallel environments?
Yeah.
For the MuJoCo case, yes. So they do perform better. I think if you use the parallel environment, but we have never tried it. So, but in terms of in the previous case, in the Atari case, there's just no way of doing any parallel, or it's just very hard to compute.
I see.
Yeah. But for the MuJoCo case, yes. So I would say that it's. Oh, actually, sorry. Back me out. So in this case, we actually use a single runner for all of the three.
I see. So this is a single worker.
Yeah. So in this case, it's all single worker case.
Okay, that makes it much more
comparable. Yeah. So this is all single worker case.
Yeah, because otherwise it's hard to separate how much benefit you're getting from.
Yeah. So this is all single worker case. It's not parallel. Yeah.
Okay.
Have you compare your method with the TRPO on the same model, the fully connected?
Yeah, so this is all on single models, the same model.
Same model.
Yeah, in the MuJoCo case, we're not using convolutional neural networks. It's just fully
But
connected.
then for the previous one.
For the previous work, yes.
So try the Atari game using the fully connected.
Yeah.
network.
Oh, I see.
So
I have never tried it, but I don't think that makes too much sense. It's
I
just.
know it's probably not beating the baseline, but just to see like how much gain is from the model itself
I
versus
see.
how much improvement is from the own method.
I
Just
see. I
trying
see.
to separate two.
Yeah,
Of course,
sure,
there are
sure,
overlaps.
Yeah, sure. Okay. Yeah. Yes.
Do you have an idea of how this compares to like PPO?
Yeah, I will show you later.
Oh,
yeah,
awesome.
yeah.
So, have you tried this on a toy domain where natural policy gradient is actually feasible to run? Right? To understand how much of a gap you're losing because you're approximating. using Kronecker
Yeah,
factors?
sure. Yeah, so you're right. So I think those comparisons are done like in previous papers where it's not an RL setting, but it's a supervised learning setting. So they do come.
And especially when
Yeah, okay, yeah, sure,
setting
sure.
where
Yeah.
we're doing the
Yeah,
Monte Carlo
okay,
approximation
you're right,
for
yeah.
static trees, right?
Yeah, you're right. Yeah,
And
that's
the
a,
other,
yeah.
the other thing I'm thinking of also is the comparisons with TRPO,
Uh-huh.
a more controlled comparison where I want to understand whether the Kronecker-Factored way of enforcing the constraint, that one up there,
Mm-hmm.
is allowing us to do better policy gradient updates
I see.
than the KL divergence, like the expected KL divergence thing
Mhm.
that TRPO does, which just
Mhm,
loses
mhm.
a lot of structure, right?
True,
So,
true.
I'm
I mean-
also trying to like pinpoint
Right,
how
right.
much benefit we are getting from a more
We're actually not enforcing that structure. We're just making that approximation.
I know.
So maybe that approximation, you're saying that approximation may be a better
thing. I mean,
better thing,
TRPO
yeah.
itself, it begins with very good motivations,
Uh-huh.
but then finally it just comes up with this quite hacky way to
approximate.
approximate
Yeah,
it,
yeah,
right?
true,
And
true.
it could well be that, yes, you are also sort of coming up with a more heuristic approximation, but
Mhm.
maybe that is more suited for our problems. right?
Maybe.
So-
Yeah.
Yeah. No, the toy example is a good point, but he's saying that it's a different in the first K-FAC paper.
Yeah, so they did those things. Yeah,
But it is but that's supervised.
Exactly.
Yes,
So with
supervised.
RL, where we, especially like the Monte Carlo updates here, have a very different bias variance trade-off.
Sure.
Right.
Right? I mean, if you're already telling me that using a moving average, which means it's a biased Fischer estimate, but it's got lower variance, and
Yeah,
that's
yeah.
a good thing for RL,
Uh-huh.
that sort of changes the landscape of the problem.
I see.
So,
Yeah, that makes sense. Yes. Yeah, that's a good point. Right. Okay. So, continuing the talk. So we also did those experiments from from pixel inputs directly. So usually it's just from state space. We also are able to train those agents directly from the pixel space for those continuous control problems. This is, I believe, is like first or second work on this type of tasks. So the previous work, only one paper, DDPG, does something like this, but they only use some very easy tasks, but where we actually are succeed on some of the MuJoCo tasks. So for example, here, like this is the inputs we put it into the neural networks. It's also a convolutional neural networks, but we are able to train it using Actor. Okay, so again, so this is some PPO results. So actually, I'd like to say that PPO is not a competitor because it's actually just switching the loss of the it's basically switch another objective. But we can still use K-FAC to optimize PPO. So this is what we do. Before that, if we just compare PPO and Actor, PPO using the normal optimization and Actor, then they're about the same on most of the Atari games and the MuJoCo tasks. Right. So PPO is actually a very good method as well. But my point is that you can still use K-FAC to do optimization on the PPO. So this is some result that we obtained at OpenAI as a side project during my internship with Jiamin Song. Basically, what we do is like switching the optimizer by using the same loss. So the green line is the Actor and the blue line is the SGD. So you can still see some of the improvements on some of the tasks, on most of the tasks, I would say. Yeah. So but one point here is that if you use K-FAC, is basically you run over the data twice, and the number of mini batch. Oh shoot, this is a typo. The number of mini batches is actually just one. So you're not partitioning your batch of data into a lot of small batches. You're just sweeping all of them, doing one update. But in the usual PPO setting where they use SGD or other first order method, they actually, after they aggregate some of the rollouts, they sort of doing like a supervised learning of training. So basically they run over the data 10 times and they partition your data into 32 small mini batches. So basically they are doing like 32 modification of the policy, 32 times 10. So basically 320 updates of the policy. But where we only did twice. So that's a difference. Like, so it's like we only use 160 x number, a small number of updates to beat PPO or to beat SGD. Yeah. So if we use the same number of updates, then you actually can see there are a lot of gaps between K-FAC and SGD. So in most of the games, in most of the tasks. So K-FAC is very, very efficient in terms of the performance you can get with one update. All right, so these are all great performance. Then let's look at how about work clock time. So it only increases 10 to 25 computation time. So like if you look at this, what I'm showing here is that the number of time steps per second. So number of time step per second, yes. So number of frames you do per second. So there is not too much differences between Actor and the A2C. So these numbers are all pretty much the same, like 10 to 25% of computation time. So one takes about like 16 hours, the other takes about like 20 hours. That's the difference. So which you don't pretty much you don't really care about. Another thing that I want to emphasize here is that we can get a lot of gain if we use large batch for doing those second order optimizations. So the second order optimization gives us basically it extracts more information for a batch of data, because it is in the same time of calculating the first order gradient, it also calculates the curvatures. So I'm showing you here is that if you compare using a batch size of 160 and 640 of using Actor and A2C, then for Actor you can get this much of gain by using a large batch size. But for SGD, you can only get this much gain here. So this is another benefits we can get for doing second order optimization. And this is something that I think current industry people really care about, which is using large batch size. So like papers like training ImageNet in like 1 hour or even 24 minutes, they all use some hacky tricks like some learning rate schedule or warm up. But I believe if you use second order optimization, such as K-FAC, then you can just get rid of that, like just works out of box, because it can extract more information from the batches.
Question,
yeah.
So for each point on the x-axis,
so for this plot, yes. So this is number of updates. So that means how many number of updates.
So each update has different sizes.
Yes.
So it's not. So if it's not entirely fair, because the trajectory has a lot.
Right. So if you look at this curve here, so this means the number of samples. Mm-hmm. So this is this. So I guess what you want to see is this curve. So basically, if you use 160 or 640, the difference is not large in terms of number of samples. But for A2C, which is the first order like SUD, it actually, if you use a much larger batch size, it just decreases. It just basically becomes crap. Yeah.
I see. So is the wall time about the same?
The workout time is about the same. Yeah.
Okay.
Yeah.
So for large, so there's no increase in computation time for K-FAC if you have a large batch?
No.
Okay.
Yeah. Okay, so another thing that I want to compare with is that if we use only Actor, for doing optimization versus what we propose is that we also do K-FAC optimization for the critic. So the only actor means like the usual natural policy gradient. So we actually can also get some improvements. Yes.
So I think the gradient of theta log is a very well motivated metric for the actor.
Yes, yes.
For the critic, did you actually try?
Yeah, we tried. We actually tried with different metric, but it turns out that the Gauss-Newton actually performs relatively the best. So we actually tried to estimate the variance. So the variance can be estimated the variance of the Bellman error. So it's just like a regression, like the variance of the noise. But then that doesn't seem to work as good as just using like one. Yeah. Anyway, so yeah. Lastly, I want to show you that because we're using this type of approximation for doing trust region, so like 0.01 is our radius, and we calculate like how the KL changes in like the exact change of KL. And we see that it's actually sort of bounding by this 0.01. So it's actually doing some reasonable trust region, although it's an approximation to Fischer. All right, so in conclusion, I present to you a method called K-FAC, which uses probabilistic model to do an approximate natural gradient. And we apply it to reinforcement learning setting, which come up with this method called ACKTR, which is 2 to 3x improvement in sample efficiency, but also only takes 10 to 25 longer computation time. It can learn both continuous and discrete control tasks from directly from pixel inputs, and is also able to use batch size more efficiently. It can scale up to more batch size more efficiently. And we find out that optimization the critic using the K-FAC is also very useful. And lastly, the K-FAC approximation helps us the trust region method, helps trust region, and also PPO is not like competitor. It's something that you can also improve upon using K-FAC. All right, so coming soon is some side project I did at OpenAI using K-FAC for Q-learning and DDPG and maybe PPO. And stay tuned. All right, so thank you. Yeah.
I think we have the room until 3:15, so we have a few minutes for 1 or 2 quick questions.
So what's your main project at OpenAI? There's so many side projects.
Yeah, my main project doesn't work. Yeah, my main project is trying to do meta-learning, basically trying to learn an advantage function, but it doesn't work. So, so yeah, like I basically spent most like 90% of time on the meta-learning part of the thing, and it doesn't work. I tried so many things, it doesn't work. But then, like 10% of time using K-FAC seems to produce some results. So yeah, so K-FAC seems really a good thing.
K-FAC has been around for some time, but
it's
not widely.
Yeah, that's the reason why I'm standing here to talk to you about this. I mean, okay, so be fair, like I think before 2017, before last November, I guess, there is not a good implementation of K-FAC. Right. So only after the Jimmy's paper, which is a distributed implementation of K-FAC, it starts to become useful. So previously, there is only this sort of very general theory, but it doesn't seem to have like a very practical implementation. And I mean, the K-FAC does have a lot of implementation techniques that go with it. So yeah, I think the main disadvantage of this algorithm is that it's just complicated to implement. It's not as simple as like Adam or other first-order method that you can anyone can just implement. Yeah, but then if Google Brain is actually developing K-FAC from last November, so they should release it soon. And I think as long as it releases it, then I think K-FAC will eventually take over the world.
In fact, essentially K-FAC is an approximate second-order method.
Yes.
So could you kind of give a comparison of different kinds of second-order methods
Right.
other than K-FAC?
So you're saying some methods like LBFGS or like those sort of like more approximated Newton methods?
And that is kind of, that's not stochastic
Yes.
one. But for the stochastic, in the stochastic domain, except K-FAC, do we have any other second-order methods, and how K-FAC?
For deep learning, for neural networks, no. So this is the first, that's scalable algorithm, scalable second order.
To some extent, we could argue that Adam is basically trying to approximate the diagonals.
Diagonal, yes.
So it's like the simplest approximation we could still have to still be first order, but get some curvature.
Basically, I have no plus some band.
But I would argue that like Adam, method like Adam won't give you too much benefit over SGD with momentum. So
tuned SGD.
Yeah, with well-tuned SGD with momentum. I think the main benefit you can get from Adam is that you don't really need to tune it. Yeah. But SGD can perform as good as Adam in most of the cases if you tune well. Yeah.
Did you implement K-FAC in TensorFlow?
Yeah, yes, it's in TensorFlow. Yeah. So TensorFlow gives you this flexibility of constructing the computation graph. So you can see that you have to extract those activations and backpropagated derivatives and then constructing some sort of matrices. But TensorFlow, you can grab those things, operators directly, and then doing some sort of automatic search of these elements in your computation graph. And it's a complicated code, but you can do that in TensorFlow. Yeah.
You mean to code it, it's complicated, but mathematically it's not so complicated.
No, it's in mathematics. It's not complicated.
Yeah.
Yes.
I'm trying to see how I can apply this to some of the policies that Matthew has trained, right? Where he uses LSTMs or.
Oh yes. So LSTM is a bottleneck. So I think, right. You can modify the code to be support to LSTM by assuming layer-wise, time step-wise independent. So you can just
also want to factor across time.
Yeah, factor across time, but basically treating each layer as a different sample, like you just aggregate them all together. You can do that, but there are more complicated way of deal with the correlation across time. That work is done by Jimmy and James Martins, which is which they should release soon, but I don't know about the details.
Okay, I guess if you have more questions, we can take the questions offline. I will be here until Friday. So that's the speaker again.
Thank you.